Hi, and thank you for joining me in this video about forecasts. We're going to start out talking generally about forecasts. And first off, we'll talk about the process, the forecasting process. The basis for forecast is that you know what the current conditions are like, and then based on the changes, you can come up with what things are going to look like in the future. A good example is on a day when the temperature is 90. If you told me that tomorrow it's going to be 20 degrees, I'd say, I don't know if I believe that. It depends on the expected changes. So your current conditions are very important in determining what your forecast will be like. The current conditions, of course, are observations. We use radiosondes to get upper air observations. We have ASOS or AWOS machines telling us what the conditions are like at the surface. And then also throw into the mix, we've got radar and satellite to give us an idea of what the weather is like where we don't have surface or upper air observations. The expected changes are based on our understanding of the physical processes of the atmosphere. Things like how air comes in, colder air comes into a region, or warmer air, or the solar radiation that's striking the ground and also striking other objects in our atmosphere. Being able to conduct energy from the surface to the atmosphere through conduction. And then also the mixing in our atmosphere as air heats up and cools down. It rises and sinks in our atmosphere. Those are all of the different types of expected changes. Also, we have other mathematical equations that tell us about how these processes occur, like as air rises, it cools adiabatically. And if it gets cool enough to reach the dew point, you'll have condensation or perhaps even freezing. Or conversely, as precipitation falls, it'll evaporate into the atmosphere. The properties that we're trying to forecast are our basic meteorological variables of temperature, pressure, moisture, and wind direction and speed. We'll move into the different types of forecasts. There's many different types of forecasts, and here we're going to look at these very generally. The first forecast we're going to look at is the persistence forecast. And the persistence forecast can be made by anybody. And what the persistence forecast states is that the conditions that you have at the time of forecast will actually persist throughout the forecast period. Basically, this is a forecast of no change. What you have now is what you'll have an hour, 2, or 3 from now. Another type of forecast is the trend or the nowcast. And the trend or nowcast says that the conditions that you have now will change, and they'll change based on the observed changes that we've seen in the recent past. So in other words, take our current conditions and add those steady changes, and that gives us a forecast into the future. This is good when you're looking at things that are not really changing very rapidly. And they are based on extrapolation, also based on statistical methods, and also based on forecaster intuition. Another type of forecast that can be used is numerical weather prediction. And NWP states that the current conditions will change with the numerical solutions to a mathematical set of equations that give us weather forecasts into the future. Numerical weather prediction came about in the early 1950s with the advent of computers. And what numerical weather prediction is, it's a simulation of the atmosphere. We have mathematical equations that describe how our atmosphere changes, and using those equations, we can time step those equations into the future to have a model of what our atmosphere will look like in the future. These simulations can vary in size from a global scale all the way down to a very small local scale. And likewise, we can change the spacing between the grid points that we calculate variables for. Most of the models that are used for forecasting across the United States are run at the National Center for Environmental Prediction. There they have a suite of high-speed computers that take all of the observations across the United States, both surface and aloft. They try to fit that to grid points in the computer models through what they call data assimilation. And then from that, those initial conditions, they try to perform a numerical simulation of the atmosphere using the equations of numerical weather prediction. The output from these computer models are used by humans as guidance. So the humans are looking at the weather information from the models, trying to figure out what that means to the weather conditions in their local areas. Numerical weather prediction is not perfect. There are problems, and some of the problems deal with the initial conditions. In other words, trying to figure out what is actually happening at the initial time. And that can be broken down into bad observations, meaning that the sensors that we have that measure properties in the atmosphere, temperature, pressure, sometimes those sensors break and we have to be able to recognize which observations are bad. If they're ingested and run in a computer model, if it's a bad observation, then you're going to get a bad forecast. Also, another problem is the lack of observations, meaning that over certain areas there may not be enough observations to really help resolve what type of weather phenomena is occurring. For example, over the oceans, there's not a lot of surface observations, or other things, other places such as in the upper atmosphere. When we're concerned about looking for areas of clear air turbulence, that's a very small scale phenomena. And as a result, we don't have really good observations of clear air turbulence. Other problems with numerical weather prediction include the grid spacing, meaning that we don't have find enough resolution to resolve every little weather phenomena, a cumulus cloud forming. That's very complex, and we don't really explicitly forecast individual clouds forming. And then another problem also is the equations that we use in the computer model are a lot of times parameterizations, meaning that it doesn't precisely depict the physics of what's going on. So it's kind of an imperfect simulation of the atmosphere. To alleviate some of these problems of numerical weather prediction, statistical techniques are used. And two specific techniques. One is where we look at historical observations to come up with kind of relationships that tell us what's going to happen based on our numerical weather output. And then also, if we vary the initial conditions, we can look at various forecasts and come up with the most probable type of forecast. And that's called ensemble forecasting. Another type of forecast is climatology. I think most people understand what climatology is. Climatology is basically the statistical data that is collected over years, weather observations over years, to come up with averages, means, and also standard deviations, and then using that, trying to make a forecast into the future. If I'm trying to forecast what the weather conditions will be like next May or next June, I can look at our climatological data and kind of get a ballpark figure. I know it's not going to snow in June or July. Well, North Dakota, maybe. How good are our weather forecasts? Well, let's not look at the specifics, but let's look at the accuracy of forecasting a little bit more generally. Here's a diagram showing forecast accuracy along the vertical axis and the forecast period along the bottom axis. So forecast accuracy increases as you go up, and the forecast period increases as you go to the right. We're going to use this diagram to explore the different types of forecasts. First, the persistence forecast. Persistence forecast, as we said, what you have now is what you'll have in the future. And that's good in the short term. We're talking minutes, maybe even an hour. But if there's any kind of changes in the weather, if the weather is not stagnant, then it's going to be not a very good forecast. And in the long term, it's a rather poor forecast. The trend or nowcast is good in the short term, but more than a few minutes or actually even a few hours, it starts to fall apart. Nowcasting is used by forecasters when there is a weather event that's occurring and they know that that event is going to continue to occur in the near future. A good example is a severe thunderstorm. If you see a severe thunderstorm off to the west and you know the predominant winds are moving from the west to the east, or you can see it on radar and you track the path of the storm, you can estimate where the thunderstorm will end up in maybe a few minutes or even out a half hour or so. But that doesn't tell you if the storm is going to fall apart or if it's going to intensify. So that's the problem with trend forecasts. It's good if the trend continues, but when it changes, you've got problems. As you can see in this slide, numerical weather prediction is actually better in the long run than nowcasting. For small-scale weather phenomena, numerical weather prediction does a pretty good job of forecasting in the really short term. But if you go out to later forecast periods, out into the future, 24 or 36 hours, it's not going to pick up those really small-scale phenomena like a small thunderstorm. It's going to be able to handle more of the large-scale weather phenomena. So the bigger the scale, the greater the forecast accuracy out into the future. And if you go way out into the future, some numerical models go out to 360 hours. They give you a hint of what's going to happen, but you don't have a lot of detail, as this figure shows. Climatologically, of course, climatology itself is good in the long run, but it's not a very good forecast in the short term. So the last thing we'll talk about is the role of the forecaster. And what the forecaster is really important, of course, in making forecasts. But they use all the products and all the tools at their disposal. They use numerical weather prediction as guidance or as a tool. And numerical weather prediction by itself won't make a very accurate forecast. You need human input to provide value. In other words, to make that forecast really meaningful. I hope this gives you some idea of how forecasts are made. And in other videos, we'll talk more specifically about the tools that are used.